second slot of this 7th BE-AM Symposium, and it's now my duty to introduce Martin Schmitz. He's working as a computer scientist, as postdoc computer scientist at TU Darmstadt, researcher at the Telecooperation Lab in human-computer interaction. And his current research interests, as I find it when I start Googling him and stalking, mixed haptics, mixed reality haptics and fabrication. And that's what his title, the title of his presentation is also adding for. It's from atoms to bits, not voxels, bits. 3D printed human computer interfaces. Martin, floor is yours. Where is he?
Thanks. Here I am. So, can you see the screen?
Yes, it works. Perfect.
So yeah, thank you for the kind introduction and also for the invitation to speak in another research domain as a computer scientist.
Yes, so, it's a different domain.
Yeah, it's always a nice opportunity to get some new thoughts and ideas from another domain. So as you said, my name is Martin and I'm heading the computer interaction group at the Telecooperation Lab of TU Darmstadt. And today I'm going to talk about how 3D printing can also transform human-computer interfaces to further shorten the gap between the atoms of the real world for printing and the bits of the digital world as we know it from computer science. So for a long time, basically computers have only been found as PCs in the office, and now are more and more interactive devices are coming onto the market, like smartphones you all know, or tablets, or even watches. And what's striking here is that these devices respond to touch, but are rather flat and like two-dimensional. And as a result, this kind of interaction is often feels like basically or physically interacting through a glass wall, but not like interacting with what you do with physical objects. So wouldn't it be much better if interaction with digital content more felt like interacting with physical objects? So imagine, for instance, that interaction with digital content had the expressive power of what you know from board games as an example, with a wide variety of game characters, for example, with interactions like moving a ship on a screen or turning a character to change the view digitally, or tapping like an animal to initiate an interaction. So this type of interaction is much more direct and physical than previous with touchscreens, but it requires a variety of precisely fitting physical objects that must be tailored to either the application or the user. But unfortunately, this video is just a non-functional vision. So why doesn't the world already look like this? What's the problem here? So basically, if you want to create an interactive object today, for example, you want to make the stack interactive, you have to use mass-produced components that are basically flat and not flexible in shape. And you need to integrate it in this complex object of the duck. And this requires novel concepts how to do this and how to shape the interactive structures and the chips to put it into the 3D printed object. And also this production is often very time consuming and manual, and also, as illustrated here, quite frustrating to do. So 3D printing and additive manufacturing is basically the perfect fit. On the other hand, that promises in principle to fully automate the production of such individual objects, as shown with the board games, or here with another example. And this can be controlled on demand and with comparatively low production costs for the object. And at the same time, a wide variety of materials, such as conductive or deformable materials, exist, so they can be combined in almost any complexity in the object. However, like 3D printing today is still often limited to passive objects. They can be very complex, and that's a good thing, but the objects themselves are often passive, out of plastic, metal, or concrete. And at the same time, modeling and the printing requires expert knowledge in designing, which needs to be trained over years. It's nothing a normal user can do easily. So how do we envision the future of creating 3D printed interactive objects? So basically, imagine you have an idea in your head. An object should play a melody on touch, for example. So how do you do that? What's different now compared to a mass-produced device that you buy in the store? So based on the interaction concepts that we worked on, such as touching or moving an object, you can personalize any 3D object in a simple design tool according to your wishes and provide it with interactivity that fits exactly what you need or what your application requires. So for instance, you have loaded the 3D model of the object from the internet or created it yourself by means of 3D scan. And when you are finished, the object is then printed fully automatically according to your wishes. So all algorithms and stuff in the background is handled automatically. And for example, it's perfectly fits to your hand or to any use case. And then we envision like two different kinds of user scenarios. The first one is the so-called on-screen controls. So this means that the objects function as an extension of existing interactive touchscreens. So what you know from smartphones or tablet or even wall-sized displays, as illustrated here. And this approach has the charm that the object is ready to use without further assembly. But of course, alternatively, the object can also be provided with electronics and the battery to work as a highly individualized interactive device standalone without requiring a smartphone or anything else. So my research domain is basically guided by this vision of an easy to use and highly customizable application environment for interactive devices. In this talk, I'm going to present to you a short selection of 3D printable sensor concepts that enable the detection of touching an object, deforming an object, and also motion or environmental influences that act upon an object. So for the first domain, I will focus on touch, so that basically detecting whether an object is touched at a certain location. As shown at the beginning, of course, it's an important interaction with the board games that you can detect touching on an object, like here illustrated with this chest. So to recognize touch, today's smartphones or tablets use what is known as capacitive sensing, and it works as follows. So at the center is an electrode here in black, connected by a wire to a touch controller. And based on the model of a plate capacitor, the touch controller can measure a capacitance, shown in red at the right, between the electrode and the finger. When the finger approaches the electrode, the capacitance increases, and the capacitance decreases again when the finger moves away from the electrode again. And if the finger gets even closer to the electrode, the capacitance increases accordingly. That's the basic principle. Essentially, this is used to measure the electric field between the plate and the finger, or the capacitance. And we utilize this principle to combine insulating and conductive filament in multi-material printing. So that is, we fabricate objects with multiple touch electrodes, for instance, that are then routed inside the object to a touch controller at the outside of the object through printed wires. So we have these hybrid objects of insulating and conductive filament. And in this project called Capricate, we use this principle to detect touch on 3D printed objects. So for this purpose, we contribute a fabrication pipeline. So a continuous development process consisting of the following steps. So in the first step, one can open an existing 3D model in a design tool, which has been, for example, loaded from the internet, and generate electrodes on it. So we have this two-step interaction technique used for this purpose. First, one roughly selects the location of the electrode on the 3D model, and then can also make fine adjustment to the electrode shape, as shown here. And often this, sorry, let me go back. Often, but not only individual touches needs to be detected, but also their position within the individual selection. So traditional approaches would use like a grid structure consisting of columns and rows. But the main problem here is that it's not suited for complex structures like possible with 3D printing. and they don't scale also to these arbitrarily shaped selections. So if you have a look here, for instance, with a 2D example, if you imagine you want to detect the exact position of a touch within this star-shaped selection on the left, and by means of traditional methods, the area within the star would not be covered by many electrodes. So in addition, electrode sizes here vary from very small at the edges of the star to very broad in the middle. And this varies also the capacitance measured, and it's very hard to detect reliably. And so grid-based approaches here are not very suited for complex non-developable surfaces. So we contribute an algorithm for generating such grids. And it first generates a predefined number of touch points that are automatically distributed in the selection, even on a 3D structure. And based on this, the electrodes are generated that corresponds to a Dijkstra distribution. So that means all those positions of the stars are assigned to the touch point to which they have the smallest distance. And with this approach, individually shaped 3D selection can be filled with approximately equally distributed electrodes. Of course, this is a 2D example, but this works on an arbitrarily shaped 3D structure of a 3D model. Just for illustration here. Based on this, then the tool or the algorithms generates the wiring inside the object. So if every electrode needs to be wired to the outside to the touch controller. And these models here simplified are then also exportable to be used in different fabrication processes. We employ FDM printing, but it's easily possible to use any kind of other printing technology that is able to combine different functional materials here. So as I said, it's here as a low-cost hardware and platform. We use these FDM processes that are not that expensive because we want to enable makers, researchers, and also users to directly use our approaches for their projects instead of requiring printers that costs hundreds of thousands of dollars. And when in the last step, we propose also some application scenarios, for example, for novel input prototypes, for wearable devices tailored to the individual dimensions of the users, or for so-called spatial interfaces that, for instance, make view information interactive with the 3D form, as shown here with the Mount Everest example. Of course, these are low-fidelity prototyping examples often used in HDI research to test new kinds of interaction concepts, but you can easily imagine that the algorithms and sensor concepts can be used also in more complex devices in the future. Research in human-computer interfaces also investigates how deformations of objects can be used to extend the limited expressiveness of touch, because touch is only binary, like to touch or not. So we try to investigate more expressive ways to interact with the computer. And in this project, for instance, we have explored deformation interactions, so such as squeezing or bending in combination with capacitive touchscreens. And these can significantly increase the expressiveness of interactions for many application scenarios by offering additional degrees of freedom, such as bending the tree or squeezing the other tree. In contrast to touch interactions, the objects are made of conductive PLA and deformable TPU in this case. So to detect these and other deformations, we propose 3 different measurement principles. In spatial deformations, it uses the position of the several touch points at the bottom here in black to determine the deformation when you press it. In surface deformation, we use the pressure-induced distance of a finger to the electrode. And in deformation inside the object, we can detect deformations such as bending via distance changes in the object between electrodes. Sadly, I cannot elaborate on our principles here. That would be too long, but I try to give you a brief glimpse at deformation inside the object and surface deformation first. So for surface deformation, we use the level of capacitance as a measure of deformation. And for this, we use the capacitive raw data from a touchscreen which is basically a matrix of gray pixels. So a brighter pixel in this image means a greater measured capacitance. So the principle of surface deformation is based on a blue flexible structure here over an electrode, which can be pressed in by a finger. That is, when deformation occurs, the material is compressed and the finger approaches the electrode, and due to the change in distance, the measured capacitance increases and then allows to infer the force exerted by the finger on the object. You can see this here briefly in an example. So we have this tube object is recognized as a circle on the touchscreen, as you can see in the top right corner. And if you press the tube, the middle point in the circle becomes brighter or not, depending on the amount of pressure you apply to the tube. So besides these surface cases, we also have like cases where the deformation doesn't happen on the surface of an object, but in the inside of an object. So for instance, in bending. So for this, we have different kinds of sensor concepts that again uses a flexible structure now in the object, and which is compressed according to the deformation. So this means that the distance between the electrodes in the object changes during the deformation. And as based on the change in distance, we can again infer the force exerted by this deformation. So for instance, here in a simple example, we have 4 distinct touch electrodes at the bottom, this black displayed here in the image. And when you place it on the touch screen, you can see the raw capacitance image at the top right again. And depending on the bending of the object of the upper part, you can see that we can infer the direction of bending with the data from the touch screen in 360 degrees. So based on these principles, we can contribute a variety of different sensor concepts that also allow to detect the direction of, for instance, squeezing, like from front to back or left to right, or different kinds of bending interactions or different kinds of pressure interactions that you can apply to 3D printed objects. One possible example for more expressive interactions in this case is like the following. You have this squeezy tube object, and by physically squeezing the 3D printed tube, the color is digitally distributed on the screen. And according to the pressure, the amount of color increases. So of course, this is only a simple example, but I think you can easily imagine how it transfers to more complex playing scenarios for construction, for instance, most likely then on larger displays, not tablet size, but more like table size displays. So as a last project, I want to give you a brief introduction to the idea of offline sensing. So one, but of course not the only application scenario here, is parcel shipping. And normally you don't know whether a package has been handled well by the carrier. Here, for example, package B has fallen ungently to the floor. You accept the parcel, but it's difficult to prove that it was handled improperly. And with the offline sensing idea, the world would look a little bit different. The shipper would print 2 offline sensors and place them in package A and package B, and later the same accident happens again. But this time with the crucial difference, the recipient can place the sensor on her smartphone and immediately see that package A was handled correctly and package B was not. So this works without a power supply during the shipping. It just needs a smartphone app, a standard smartphone app at the end to read out the internal state of the object. To do this, offline sensors irreversibly change their internal state based on a specific interaction without the need for electronics. So in this change of state can be read out via a capacitive touchscreen as follows. So you have this capacitive touchscreen at the bottom. And for this purpose, an offline sensor has 2 electrodes. One establishes the connection to the finger and one to the touchscreen. And if the offline sensor is placed on the touchscreen without a change of state, as in this case, there's no connection between the finger and the touchscreen through the object. And now if a change of state, it's abstract for now, happens, for example, a conductive medium is placed between the 2 electrodes, which was not there before, and only got there because of the interaction, then this leads to a capacitive path, which leads then again to an increased signal of capacitance compared to the initial state, and this can be read out. And based on this principle, we can recognize a variety of interactions. There are, for example, flipping over, tilting, pressing of an object, or acceleration, but also interactions such as loading or states of the environment, such as freezing below or heating above a certain threshold. And such offline objects might also be integrated in bigger printed structures for decades. So they can maybe govern certain correct use or check that environmental conditions were held all the time. I don't have that much time anymore, so I give you a brief glimpse on how one example of a sensor works for tilting. You have different kind of chambers, and in one chamber there's a conductive liquid, and if you turn the object around, the liquid flows in the other chamber and connects the two electrodes at the right with liquid, and then this can be read out. It's simplified here, but this is the basic principle which operates here for tilting. Of course, this is also possible for pressure sensing. If you squeeze like the object above a certain degree, the liquid flows around and then connects in the circular upper part the two electrodes. There's also a verification pipeline behind there, so you can easily specify the sensors and then print them fully automatically and use them. And I would like to end my talk now with a few impressions of one of my most recent projects that show how 3D printed interactive objects on commodity touch enabled devices can transform our style of interaction with computers in the future. So all objects shown here are 3D printed, but in a single pass without requiring any additional assembly or internal electronics. So all sensing and processing happens outside of the object inside the touchscreen. And I think this example quite neatly illustrates that AM is perfectly suited to further fuse the digital world of bits on the one hand and the physical worlds of atoms together. And this allows highly customized interactions that are specifically tailored to the needs of users or application scenarios, and offer great potential for more expressive and direct and natural interaction with computer systems in the future. So thanks for listening, and if you want to contact me, feel free to visit my website at schmitz.org, and I'm happy to answer any questions. Thank you.
Thank you. I do a quick one as we were a bit behind schedule. You have one with free, money doesn't count. What do you want to get printed for this interaction in our built environment, in our buildings? What was your first idea of where would this help to use our buildings better?
Inside the building, what's the most obvious thing is like before in the construction and in the design. I guess this could be huge to print different parts of smaller architectural structures and to combine them on a touch screen, like to place in an environment, or use it with augmented or virtual reality. So I guess it can vastly transform the way you do like the steps before the actual construction. Inside the building, I think that's the reason why I thought I need to present this offline sensing idea in principle, because they're specifically equipped without electronics and without anything that needs a power supply. So you can place them in a wall or in a building, and it could govern if it's heated up or not heated up, or if it's statically used well. So I think this smart sensing structures inside buildings that don't need electronics during the detection is a great potential here.
I fully buy in. Tracking, say, the action of a building for a long period, and as I don't need any electricity, any current, that could last for 50 years.
Mhm.
and you then could track certain impact. That would be really an interesting one.